been on the Canvas site for some time and just bring you up to speed with the different methods that are available, or at least some selected versions that I've compiled in that handout. I would say it's quite a few methods presented there. Today, there'll be an overview of settlement after we finalize stress distribution and move on to immediate settlement, specifically for footings on clay. And there is a technique for that. Next time, we'll look at footings on sand, and there's a technique called the Schmertman method or Schmertman technique that we will evaluate. I don't think we'll get to that material today, but we'll see how timeline goes. Due to a medical appointment at just after class, right after, I need to cut out today about 5 minutes early. So just a heads up on that expectation. I will do a new share at the moment with the stress distribution. And again, this is available on the Canvas site. We have seen this. This is the Boussinesq case, which elastic theory and semi-infinite half space, highly idealized, normalized dimensions, all the, call it regular type stuff. And this one is for a uniformly loaded rectangular area. That's reasonable for a lot of foundations, but not directly on target, but we certainly need to make some simplifications and assumptions as we go along. And this isn't bad. So this is a nice upgrade from, say, the 2-to-1. And we went through this last time and did an example for both the center of foundation and the corner of the foundation to show you how that compares. And an important takeaway on that is that you establish the loading at the surface, and that remains the same, meaning that stress remains the same. And then you take little pieces of that, either the whole thing to get to the corner, and then you're utilizing the chart directly, call it as intended. And if you want to do the center point, you have to subdivide that into 4 little pieces. And you're still utilizing that same pressure that's acting on each of those 4. And now you have different dimensions for those points. Let me compare this to the let's see here. There are plenty of equations that you can utilize to do this as well. And seeing that the author of your text, Salgado, is quite a mathematician in spirit. He's pushed that end of things quite heavily. And I would like to share with you that version. I'll just show it to you because it's directly out of the text, so I don't expect for you to be writing it down and digesting it here, or me taking the time here to present it. But I'd like to at least share it with you so you have exposure to it, as you may utilize it as we go along in the course for reason of establishing a spreadsheet with calculations for settlement. And I'm envisioning that being appropriate for, say, your design project towards the end of the course. And what we have here, this is a little dicey on for whatever reason, focus. But in any event, it's page 156 of your text. And you see this long equation here. And this is for the uniform pressure distribution of a rectangular area. And this will provide the stress under the corner. So sigma 3 corner is the vertical stress under the corner and shows this large equation. And it looks reasonably, say, harmless, except you'll see that embedded within here are M and N. Those are familiar from the M and N chart that we've been using with Boussinesq. And you'll also see a C1 and a C2 embedded in the equation. And if you make replacements for those with what C1 and C2 are, which is on the next page, page 157, expression, it's extremely handy to just grab numbers directly. Of foundations, it is quite efficient from that standpoint. So I'll go back to the chart version of this, which I generally like. I mean, from, if you're just doing one problem and so on, I think this is a very nice way to approach it rather than try to tackle it with that equation I just showed. But the equation, as I mentioned, does come in handy for programming when applicable. So next up is an analogous chart. It's more or less the same chart, except it is using what's called the Westergaard theory. And Westergaard, different than Boussinesq, came in with some different assumptions. But the nuts and bolts, how the chart operates, M and N are the same, B over Z, L over Z, and so on. Everything remains the same. Weightless soil, semi-infinite half space, elastic behavior, and so on. But Westergaard added a layering of infinitely stiff reinforcement layers into his analytical solution on this. And it has been documented to work quite well for layered soil conditions and may be appropriate for locations where maybe you have reinforcing layers in place, such as a geosynthetic system supporting a foundation, which most certainly is a common occurrence or can be designed in that manner. But the rest of it remains entirely intact. I would say Boussinesq is probably more the go-to technique, more the default, but Westergaard is absolutely available. I'll show a comparison of the two in just a minute, actually right now. On this, we have, what happened there? I tried to rotate it. Didn't like it. Well, I'm sorry, it's not rotating. I'm trying to, and it is not doing it. So I'm trying to go clockwise. I'll try to go counterclockwise just for fun. That didn't do it either. Okay, in any event, I'm gonna have to return your head if you wanna see it live on the screen. You have the handout, so you can check it out anytime you like. But this is a table now of stress beneath the center of a foundation, so that superposition of four little elements has been done for you in this case, and directly from this table you can grab numbers for values associated with different depths under the center of the foundation. And a neat thing about this table, both of these on this page, by the way, is that it compares side-by-side assessment of the Boussinesq and the Westergaard solutions. And you do find that there's considerable difference in places. I mean, here we have a 51.51 as your influence factor versus 0.33. So that's considerable. I mean, that's going to make a difference on settlement calculations, most certainly. And in this domain, where you have two entirely separate techniques, it would be appropriate to simply select one and justify why you're doing so. I don't feel personally that it would be appropriate to be averaging these because they are entirely different formulations and have different assumptions in place. And, you know, average doesn't quite make sense, I'll say, from a justification standpoint. What we have here is the vertical stress change under the center of a long, infinitely long strip foundation. So this will, again, you could arrive at this table by just utilizing the graphs that were on the past 2 pages. But it's been done for you here, and it's, in a sense, quite simple access as for those points of interest. Next up is something called a pressure bulb. And a pressure bulb is a neat approach in that it brings in flexibility on 2 dimensions. And what's going on here is that we have a square footing shown on the left. We have a continuous or a strip footing shown on the right, and normalized type dimensions, Z over B, and B is up here, your width of foundation. That's our good old capital B. That'll stay intact for the whole term. And in a sense, this one is square, but for the moment I'll talk about it like it's a circle just because it's easy to use the word diameter. And you might be a half a diameter below the center of the foundation. You might be 2 diameters below the corner of the foundation, and so on. You might be 3 widths B below the center of a strip foundation, and that's going to put you here. You might be midway between the center and the edge of the strip and 1.5 times the width of foundation downward. And it's all, as I said, normalized with that dimension B because this vertical axis is associated with that divided by B. So if you're 2 widths below or 2 diameters below, we could call it, you'd be down here at the 2. If you're 1.5, you'd be at this point, and you can be any number, of course. You can interpolate to any kind of number. I'm just picking some easy rounded numbers for discussion. And when you arrive at a given point of interest, let's say you're right here is your point of interest, where the cursor is, you're simply interpolating on a curvilinear scheme that is provided here, and where I'm pointing to would be something like 0.26 or something like that. It's just a interpolation by observation, and it's curvilinear type interpolation that you're doing because it's a family of curves that would continue in that general same shape. So, and of course, you're limited to some degree how much precision you could get to. I would say probably 2 decimals is all you're going to be able to wring out of this kind of graphic for precision on your influence factor. But that shows you very quickly what the number is. What your stress would be at a given location, and it brings in, importantly, the ability to move around to different locations under the footing, meaning corner or side versus center and so on. That kind of thing gets accounted for with this graphic. Next up is the Newmark influence chart. That's this one down here, and I don't have material for that prepped at the moment. Maybe what I'll do is print this, and during a break I can hit that one with a graphic superimposed over it that'll make more sense, and I will show that to you. I won't take the time right here without that being prepped. This is the next one, is the 2-to-1 method, which we've been through already. We've seen that. Next up is a circular foundation, and I think I had discussed that last time in terms of being a petroleum tank or something like that, where the curvilinear features remain the same as the M&N chart, meaning the use of this chart is quite similar, where in this case you have the numbers on the curves are x over r, so a normalized distance away from the center of the circular loaded area, that's x, as compared to the radius. And the y-axis on the plot is z over r, so it's how many radii are you below the loaded area. And again, the change in stress would be identified with an equation like this that can either be written as sigma z, sometimes presented as a delta sigma z. Both are correct in the sense, in the capacity of actually developing the chart, because this is coordinated or established using weightless soil. Next up is an embankment loading, and an embankment highlights the importance. I think I mentioned this last time, but worth repeating most certainly. It's important to read the caption when you're utilizing these and making sure that you are indeed following the intent of that given graphic. And what we have here is the influence values for a vertical stress under a very long embankment. That means length into the page being infinity. And we have an A parameter, which is a horizontal projection of the slope length. And we have a B, which is the distance of the top bench of the embankment. And what is shown here in this graphic is exactly what is in fact being modeled. It would be for, I'll call it, half of an embankment. And I'd like to go through a little bit of iterations on this, of how you would handle being at different locations under an embankment, an exercise that you will have some experience with in a homework. I think it's homework 5. So this is what is intended for the use of that chart. And if you happen to be interested in a point down here below the surface at some depth z below the base of the embankment, you can figure out A, B, and Z, and you're off to the races on that family of curves and doing the same interpolation I was speaking of on the other charts. And if you happen to be right at the middle, at the center line of the embankment, let's call it, you would enter the chart once to get the left half shaded with diagonal lines, and you would enter the chart once for the right half shown in light color here, just solid white. And as it turns out, you can, as an engineer, save some time and just say, hey, these are going to be the same. They're mirror images of one another. We'll just take the influence factor for 1/2 and multiply that by 2. And does that make sense? Indeed it does. And we can see that on this graphic up here for A over Z, B over Z. So our maximum is going to be below that center line. So we're going to be looking at regions of having high A and B values. So that would put us on the high curves here, up in this region, the high B's, and it would put us on the high A's over here. So our influence factor in this chart is the y-axis, and we're going to see we end up with an influence factor for that, what is shown in the graphic here, 0.5. And that's the rationale on this being appropriate, that you can simply multiply by 2. And if this is indeed a big embankment, and A and B are in fact large, having a point right down here under the middle should result in an influence factor of 1.0 or close to that, because what is happening is this is acting simply like another soil layer on top that doesn't even have influence factor associated with it. It is just an entire new layer being the same distribution, same stress all the way with depth, so not even being distributed at all. So that's one version. Another one would be, what if you're interested in a location off center? In this case, you could enter the chart once for the green banded area and once for the polka dot area. And you'd see you can add those two. You'd get an influence factor for 1, you'd get an influence factor for 2, and it's the same general methodology that we were using with the M&N chart, where you superimpose and sum the influence factors. The key is, at the end of that process, A, you have to make sure that each time you use the chart, you are using it in the intended manner. Usually the caption for the figure tells you if that's the case. And B, you need to, at the end, have the summation come back to what the real loading situation is. So these two are reasonably straightforward, given the framework for the graphic. Next up would be a location outside of the embankment. You might have a point over here of interest. And how are we going to do that? Well, this is like the M&N chart. We actually artificially extend that embankment out. And I'm talking here about the hatched red area. And at that point, we have a vertical line here, and we have a slope over here. So we could indeed enter the chart, for a given A, the slope length, and a B, which is going to be quite a large value in this case, because it's that entire top, including this virtual component. But that's fine. You're following the instruction or the intent of the graphic. And that would be a positive impact. And we've now overshot this. So like we did in the M&N chart with rectangles, we actually have to take out this portion that was overloaded and not really there. And hey, conveniently, it's the shape of an embankment. It happens to be upside down, but the math still works out the same. So we actually come back with that portion, black vertical hatching, as being negative. And you get an influence value here, you get an influence value on the second one, and at that stage, you sum those two and utilize the Q times, the Q in this case is gamma times H, which is a compacted unit weight of your embankment times the height of the embankment. And one more iteration, kind of the worst case scenario from a logistics standpoint of using that chart, would be the case of being somewhere mid-slope. And there are occasions where you need this. And as I said, you'll be doing something along these lines in a homework. But there are practical problems, most certainly, where you need to know the stress distribution all throughout here. And can we utilize what we just saw in these slides, or these images, I should say, to have something work here? Are there suggestions from anyone on that?
Maybe we do 3 embankments.
What the fuck is that?
I'll come back to the share, but I need to give you the heavy eye here. Make sure we get a response on this. Any ideas?
Professor, someone did respond.
Can we superimpose stuff here to make this work? I've actually started for you already. I've started the process with that little horizontal line as a bit of a hint in that regard. But if we're interested in this point down here,
Professor, can you hear us?
some point of interest down there,
Nope.
what can we sum together such that each time when we enter that chart, we're using it for a half of an embankment, let's call it, just, you know, the one side of an embankment.
You can't hear us. You can't hear us.
I'm sorry.
Can you hear me now?
I can. I'm sorry.
Okay.
Was a whole bunch of stuff being said? Probably. Sorry about that. Boy, I had my volume down. Sorry. I was talking away. I didn't have the mute on. I checked that, but oh boy, what an oversight. Too bad. So where are we at? What can we do on this one?
Can you cut the embankment in half, like where your dashed line intersects the slope? And then, okay.
And then what? That's Lauren?
Yeah, and then like do it so you have like your AB for the top half and then just your AB for the bottom half.
Top
Like-
half, this little guy, the little triangle?
Yeah.
Or
like, because you'd have your A from the far left side and then your whole B. And then
Okay.
would you
so
subtract?
that would be this big piece. What you
Yeah.
just said there is a huge piece here, which
Mhm.
indeed is A over here, and B is a real big one,
Yeah.
inclusive of that little fake triangle. And then what?
You'd like cut the embankment in half, and so you'd have like half of that A and all of B, and then the other half of the A and a longer B. But then you'd have to subtract like that part of the triangle.
I'm not getting the cut the embankment in half part. What are you addressing there?
Would you like cut the embankment in half where your dashed line, your vertical dashed line, like intersects with the embankment so that you'd have like,
We are
Yeah.
cutting there, and we
Okay.
actually addressed one half of it. I'm using the word half liberally.
Oh,
It's
no,
the left side of it. There's not
I-
a need to further cut it up.
Okay.
That will cover it. That can be taken as just one big piece, because the chart that we utilize drops out for just that, call it half. So it doesn't know that there's another little piece over here, or if it's a whole nother equal size piece if we're at the center line.
I think she's saying to cut it horizontally so you have a shortened embankment along the top. That's the regular
Right here.
shape. Yes.
Yeah, that's what I meant, but now I don't feel so good about that.
It's actually on target. So you do need a cut of some sort there, but we're not going to run it through the entire embankment. What we can do, though, is at that location, identify this right piece that I'll put with red polka dots. And that's a possibility. Now that's going to have an A, and what's going to be the B value on that one?
0.
0, correct. And that's fine, that's valid. The chart is set up to deal with zeros. So in this case, you'd have a B value of 0. So at this point, we had the pencil hash, broad hashing with pencil being inclusive of that little triangle there as a plus value. The red polka dots as a plus value. And now are we back to where we started? Are we actually what we've loaded that thing with, or is there something goofy still going on? This isn't quite correct yet. This isn't reality of how we've actually loaded that site.
You'd also have to subtract the like small top triangle, right?
That is correct. Thank you, Lauren. So you would come in here, and I'll show that with hashes going the other way. And it's again upside down, but that's fine. The math works out. And in that case, you'd have an A value, the slope, and a B value again of 0. So plus on the whole big left side, plus on the red polka dots, minus on the blue hash. Any questions on use of that embankment chart? I will expect that given that we went through the M&N and how to interpolate and so on a chart like this, that you end up at a certain place and shoot over and grab an influence value, that you generally have the routine on that. What is going on in these problems of a little bit new wrinkle for us is that Q value is the full height of the embankment. And when you are among the main bench of the embankment, I'll go back to the drawings for a sec here. When you're anywhere in this mid region, it is in fact gamma times H, where H is that embankment height, distance between the two pins. If you get into these little subshapes off here on the slope, where it's not full height of embankment, an important aspect here is that you actually shorten your H to be just this high when calculating that Q. So for that red polka dot, the Q naught would be associated with this little stress amount here. The full height of the embankment being modeled, and in this case, it's just that little triangle being modeled for that one entry into the chart. And that would be your value. So Q naught would be associated with this little h times the gamma of that embankment soil. Any questions on this embankment chart? It's one of the more involved ones, I'll say. But it's a handy thing, as this is an extremely common geometry for transportation works and so on. You could envision railway embankments, highway embankments, freeway, entrance ramps and so on. A lot of things taking on this shape. Preloading applications, which is a ground improvement technique. There's a lot of applications that will bring in the geometry of an embankment.
So just to clarify with that last scenario you showed, so first we would just do the normal, we would find the normal influence factor for that whole embankment. And then we would find the influence factors of those small triangles without the B values.
That is correct. Yeah.
Okay.
It would be with a B of 0. So you'd be coming in here, and where does B of 0 show up? Right over here. B over Z of 0 is this last curve here. So that whole last curve going up here is associated with that B equals 0.
Okay.
All right.
What would you do if we were considering an embankment built on a slope?
If it's important, if you really needed good numbers, you would probably go to a technique beyond something that is in a chart solution like this, such as finite element analysis.
Okay.
I would expect you could probably simplify the geometry to make it work here and get a good estimate. Not 3 decimal kind of precision, perfection on that, but also probably good enough to work with for design purposes would be my guess. But if it is a critical application and you're placing, tunnels or something like this, and you really need to know precisely stress values and so on, you'd take it to another level of bringing in some numerical modeling on that would go beyond a chart like this. I've never seen these charts adapted for further complexity in geometry. I've only seen them for horizontal ground surface. And that is sort of a starting assumption in all of these. I have not shown all geometries to you. I've seen charts that are established for just triangular loading, kind of like what we're talking about here, where you can actually use this chart to do it. But I've seen some standalone charts that work with a wedge type load and other geometries like that. So there are additional type graphics and charts and tables and so on available for this kind of thing. But I feel that this 7 pages worth is a pretty good summary of what is available. And I'm decidedly pushing the charts you'll see in this handout. And Salgado, in his coverage in the text, is almost entirely equations. I'm actually quite surprised that he has none of these present in his book. I think these are very, very handy. These are all out of the Naval Facilities Command design manuals, NAVFAC DM7. And that's listed in the syllabus, by the way, as a recommended reference. I'll pitch it again as being a good PDF for you guys to grab for, your careers, for PE refresher and sort of things like that. They're great resources. This is a great example of it. This is, one-stop shopping. It's everything that you need to use that chart is on that page. And you don't need any further resources or anything like that. It's just spelled. Once you know how these things work, you can actually enter this thing and use that page alone to do that. This technically is out of Holton Kovacs, but it's a printout from the NAVFAC. Much of what is presented in these 7 pages is from that manual. Questions? Any further? Okay, sorry for having the volume down. That was my bad. I will move along to settlement now and identify first an overview and big picture on settlement. Now we've addressed with this past unit what stress distribution occurs in soils due to loading at the surface. And for that matter, we understand at this stage of the course that foundations are oftentimes embedded under the ground surface, and you actually need to account for that. And you would modify your dimensions accordingly, such that when you utilize the charts, you're talking about distance below the loaded area. In other words, distance below the base of foundation would be what it is. They're, again, set up in a highly idealized, calculus kind of solution, very, very idealized stuff. And it'd be impossible to come up with solutions for every single possible foundation depth and so on. But as engineers, we just step in and cut that corner and say, all right, well, it's embedded 3 feet. So now we're 10 feet below that point of interest, which happens to be 13 feet below the ground surface. And that is not all that important for the calculation of this. But in any event, with these, you now have, stress changes, and the foundation will impose stresses. The soil, in turn, will produce strain, and an accumulation of this strain produces displacement or settlement of the foundation, downward motion of the foundation. And this can be problematic, if it accumulates to a degree of causing trouble with a building or safety concerns. Safety or economic concerns for that matter. The principal mechanism here for settlements is rolling and sliding of particles. It is not an elastic modulus. These mechanisms, sliding, rolling of particles, are not elastic. These mechanisms do not store energy, and they are the displacements experienced are not recoverable, indicating that if you take a load, away from the loaded area, if you remove the load, little if any rebound will occur in those systems. And we're going to simplify or complicate matters depending on your perspective on this. We're going to modify expectations from what is actually occurring to how we calculate this with different assumptions. We're actually going to utilize elastic theory for settlement calculations. And that is simply to keep things manageable. And, we'll call it that the results that will be evident from such an analysis are fine. They're of reasonable accuracy to work with and move forward for design purposes, but we are not modeling rolling and sliding of particles. That gets into all kinds of mathematics that's well beyond the call of duty for trying to assess settlements for regular type foundation design. Elastic parameters that we're going to utilize in this are not true elastic parameters of the soil. So to further dilute things a little bit, these are correlated from in situ tests. That would include the standard penetration test, possibly cone penetration test, flat plate dilatometer, pressure meter are some possibilities. And a drawback of this is that you're typically determining the modulus in the horizontal direction, and that is most acutely evident with the dilatometer or pressure meter, where you're actually pushing the soil outward horizontally and measuring its stiffness in that direction. And vertical is actually what we're interested in. We want to know about vertical settlement, how the foundation is going to move downward. And as it turns out, soil is anisotropic. So this is a rather complex problem. And I want you to recognize that we are indeed cutting some corners on this. And that's, it's fine for getting through a design type thing. But again, I will highlight, in similarity to, I think it was Evan's question about what do you do with a slope? What do you do if you really, really need high level refined results? You go to another level of actually modeling things with more sophisticated assumptions, analyses, and methods. categories of settlement that come into play. One is distortion, which is shown below, by the way. And I'll back up just a little bit so we see all of it at once. One is consolidation. And I'm assuming that you are familiar with that from content in 381. You'll be seeing it again here. But that should be mostly review. We'll be looking at in great depth here for, first time, let's call it, at time rate of consolidation. But magnitude of consolidation should indeed be review kind of stuff. And secondary compression. So this would be a type of settlement associated with the mechanism called creep. And these three mechanisms will sum distortion, consolidation, and secondary compression to be a total settlement. And I've allowed the terminology from Salgado to remain intact for this expression, just so that you have a paper trail between the notes and the textbook and so on. And I am astounded at Salgado's, I'll call it, poor choice of variables on this. W is water content and soil mechanics, worldwide. That is non-negotiable. Small w is water content. And now he has two things going on with this, which isn't that deadly. I mean, we can understand the context and so on of what's being talked about. But I think that it really is an unusual choice of parameter. Quite often you'd see an S for settlement, and I'm not sure what Salgado's beef with the letter S is in this case, but he simply didn't want to use it, I guess. In any event, I think we'll see beyond that. Distortion is a mobilization of the soil looking something like this. And this would largely be described by immediate type settlements. And we will be looking at that as we go along here. And this seems a good time to grab a break. So we can do so and grab 10 minutes.